we can't do it in the minute that I'm going to have this slide up here. Let's just try to understand what all these things are. So what we have is we start out with an oriented graph. So think about something like this. Okay? And then on each node of that graph, we have some domains. The domains are where the continuous dynamics of the system evolves. Okay? So this is your phase space, for example, for a mechanical system. All right? We have a set of control inputs we can apply on each one of these domains. We have a set of reset maps that tell us how the velocity changes when you switch between domains, or in the case of walking, how it changes when you change the number of contact points. And then finally, we have a vector field, or actually a control system on each domain. So that tells you the dynamics of the system and how you can affect them through control. Okay? So when you break down these different elements, it's not that complicated. Okay? And to kind of get a feel, just look at this picture. We have 4 domains here, connected by this oriented graph. We have contact points in force, so what we can do is look at the mechanical model of this system, just by using Lagrangian methods to model this, basically pendulum, right? And we get equations of motion for that system. That gives us our control system. And then we just need to know how to change the velocity of the system as the number of contact points change. So that's kind of an overview of the mathematical structure we fundamentally deal with bipeds. So again, the main point that you should get away from this is that the graph and the set of contact points completely determines the mathematical model. You can actually show that. So all we need to worry about is the graph and the contact points. Okay, and all this other stuff falls out. So let's kind of go for that. But first, let me show you a couple examples. So let's consider a couple bipeds. So we'll start out with a really simple biped. So this biped is just 2 links. This is actually called the compass gate biped. And basically, since it's 2 links, there's no knees, there's no ankles, there's nothing complicated. All you can do is basically straight legs, impact, straight legs, impact. Right? So there's only one sort of discrete event that can happen, and that's the foot strike. Now, if you add knees to this robot, so now we have 3-link pendulum. Okay, we get the dynamics for a 3-link pendulum, and we have 2 things that can happen. We can have the knee locking, and we can have the foot strike. Okay, so we can have straight leg, knee lock, foot strike. So you can see me trying to do this walking. It's not going to be very human-like, right? But we can even bump this up even more and say, okay, let's add feet and knees. Well, then we can get a lot of things that we can do. These are just 2 examples of the choices that we can make as the system evolves forward. So these are actually both things we've studied. So for example, in this case, we have heel strike and the back knee breaks. Then we have toe strike. Okay, then we get toe lift and then knee lock. So what you're doing is enumerating the possible things that can happen throughout the course of walking. So these are the discrete phases of walking. And the point here is that you can actually get 2 different ones for this walk. In fact, actually you can get a lot of them. There are a lot of possible contact points, a lot of possible models, and there's no real notion, or there wasn't before, on which one of these to pick. How to pick this ordering of events through walking. And I claim that picking this ordering of events to be human-like is the most important thing in designing mathematical models of robots. Okay? And so the idea is to look at human data to decide which one of these many options that we have we should pick. Okay? So that's kind of an overview of where we're going. So we go to get some data to actually figure that out. Which one should we use? So I went to Berkeley this summer, and they actually have a system set up that has LED lights. You can see them here, actually. This is me, because everyone else is confidential, so I get to go up there. That's me wearing a little spandex suit, which is very sexy looking on me. And with lots of LED lights telling me where everything's at. Okay, so what they had is 6 cameras hooked up, and they read the positions of all these LED lights. And so I'll show you an example of a step. We set up a line to walk on, and then we walked on this line. We did this 12 times, just walked. Okay, so it's not a complicated experiment. All right? And after we did all that walking, we got all this sensor data from this. A little slow, but this is what it looks like when we actually had to deal with it. Now you can see the LEDs. Now this dot here is actually when we drop sensors and we throw them to the origin. So you get a lot of dropped sensing actually. Almost at every given time there's sensors that are dropping in and out of contact with the cameras. Okay? So we have our basic data set now. Alright, so what do we do with this to get some useful information? Well, what we need to do is determine the contact points, as I said. Okay? So what we want to do is we're going to look at the data for the heel and the toe, because that's all that matters in terms of contact points. So the question is, through the course of a gait, a step, what contact points are in contact at any given time? So we actually look at the data itself here after we've smoothed it and done a bunch of analysis on it. And you look at it, and what do these look like? This is kind of the main idea that went behind determining all this. See, the functions are actually very simple that our heel and toe follow. So this big bump is our heel, and this green line is our toe. And the heel actually pretty much follows a Gaussian, right? And the toe is pretty much a fourth order quadratic, okay? And you see the lines when they're essentially zero, here and here, are when they're in contact with the ground. Okay, so we can actually just say, all right, let's just fit some functions to this simple functions. In this case, we fit a Gaussian, and we fit a fourth order quadratic. And then we can determine when the contacts are zero and when they're not, meaning when your contact points are in touching the ground or not. And it's actually, why are we doing all this? It's actually not obvious, because you think, oh, it's this threshold. You can't do that. The data is really noisy. There's drift in the sensors. There's lots of complicated stuff going on, so we had to extract, sort of the simplest form of the functions we can. So doing that, we can actually say, all right, we know when contact points change. Okay? Meaning we know when the heel lifts, because it's when you switch from this Gaussian to this flat line. We know when the toe contacts, because it's when you finish your fourth order quadratic. And we can say which contact points are ground at any given time, and go through the gate and figure that all out, labeling the contact points. Okay? So in the end, we did this with the 9 people that participated in the experiment. Actually, we did it with 10 people, but I'll explain that. This is only 9. I'll get to that later. It turns out one person actually didn't follow this breakdown, but they actually had surgery a couple weeks before the experiment, and we picked up on that. I'll explain that later. But out of these 9 people, we found that every single person had the same order of events throughout walking, which was rather surprising, actually. Which means there's a single, discrete graphical structure that humans seem to follow when they walk. And these people ranged from 19 to 77, from 130 pounds to 200 pounds. I think 2 people were 200, me and somebody else. From 5'6" to 6'3". So we actually had a big spread. We had 4 women and 6 men. So we went all over the place. So this was really cool. So the point being now is we should design bipeds that have this order of events. And this will actually help dictate the controllers and everything with the model, the mathematical model. So we've effectively connected human data to the mathematical model. All right? So let's kind of bring this back to a real biped, since that's what we're fundamentally interested in. I'm not a biological person, so I want to get away from biology as quickly as possible once I have the information I need. So let's consider this biped here. And we can kind of represent this as a bunch of point masses on a kinematic chain, as you would when you're modeling stuff in classes. Now, what we can do is we can begin with this human structure, and I'm going to cheat a little bit here, and we're working on fixing these cheats later, right? But the cheat is we're going to add in knee lock, okay? At least with these results. We actually can not necessarily add in knee lock, but that's very new stuff. And we add a knee lock because it's much easier to obtain walking with a biped when its knees locked. Because when the knees don't lock, you have to worry about controllers that do all this fancy stuff. It really makes it more complicated. So you add a knee lock, and we actually just get, well, we have the same number of contact points at any given time with the feet. So this is our bipedal robot model, okay? And from this model, we can get a hybrid system, okay? So I'm not going to go through all the details of that, but basically we have a graph, right, from this structure. We have a bunch of phase spaces, or configuration spaces, from the different angles that are active at any given time on the domains for the robot. And you just use this stuff, and you use Lagrangian modeling to get the mathematical models. This is all stuff that I should be able to assign you guys and you can do, right? Being grad students in ME. And then from there, we get control systems based on the dynamics that we derived. And finally, we get impact equations, which are much more complicated to construct, but I'm just going to glaze over that. But we get impact equations. All right, so let's make this robot walk. Now that we've constructed this model, we've kind of motivated the robot. Okay, so first what we're going to do is start out with 2D walking. And we're going to break up the walking into 2 dimensions and 3 dimensions. Okay? Because it turns out that it's best to separate these things. Basically, the human, when they're walking here, do very specific things. And on the side motion, it's a lot of stabilization. Okay, so we're going to break this up. So starting with 2D, as I indicated earlier, we're going to use controllers that are passivity-based, that are based on this idea that mechanically walkers walk down slopes naturally. Okay? And then we're going to add in some local controllers to kind of beat this up and make it work. Okay? So, let's start here. First, what do I mean by sagittal walking? Again, all this means